An oil company is trying to develop a reasonably priced gasoline that will improve gas mileage. 3 different types were formulated and now need to be tested. 5 cars, all of the same model, were randomly selected for each type of gasoline. Each car was driven under normal conditions for a specified distance, and the gasoline mileage was measured for each of the 15 cars. The results are below. So we have 3 types of gasoline: type G, type L, and type R. Each type of gasoline was tested on 5 randomly chosen cars of the same model. Determine whether any of the gasoline types have different effects on the mean gasoline mileage. Use alpha equal to 0.05. Okay, we have 3 populations here, and we're going to use the sample averages to see if we can prove there's a difference in the population averages. So I might let my null hypothesis be H sub 0 mu sub G equal to mu sub L equal to mu sub R. So I'm assuming there's no difference in the population averages. And the alternative, if I can reject the null, would say that at least 2 of the population means differ. I'm going to run this test at alpha equal to 0.05. I'm going to use the ANOVA procedure, and I'm going to use software, Excel, to do it. So we have Excel open. I'm going to Data, Data Analysis. I'm going to select ANOVA Single Factor. My input range, I'm going to click and drag across the data, including the labels. So I'll check the box of labels. My alpha is 0.05. My output, I'll have the upper left-hand corner of the output here in A9. Select that and then run the test. Okay, so I get a summary table of the sample averages and variances, and I get the ANOVA table. The most important value in the ANOVA table is the p-value. The p-value is 0.0010764, and that's less than 0.05, our level of significance. So we can reject the null hypothesis and conclude that there is at least a couple of the population means that are not the same. By the way, we could also run this test by taking the F value, the test statistic from the F test, and here it's 12.74, and compare that to the F critical value. This is a number we would get in the F distribution table, or at least approximate, 3.885. Since 12.74 is greater than 3.885, I would, of course, again, reject the null hypothesis. So I have the p-value equal to 0.00106764, which is less than 0.05. Reject H sub 0. Conclude that at least 2 of the population means are different. Now the question is, where are the differences? This is where we start to make pairwise comparisons. With 3 populations, the number of pairwise comparisons or combinations that we're going to have to make is C, and that formula was K times K minus 1 divided by 2. For us, K is equal to 3, so 3 times 3 minus 1 divided by 2 is equal to 3. We have 3 pairwise comparisons, and to run tests on those, we're going to use confidence intervals. If we are computing 95% confidence intervals for each one, we are 95% confident that each individual pairwise difference is contained in its respective interval. However, we are not 95% confident that all of the pairwise differences are simultaneously contained. Actually, we'd be less than 95% confident. What we need to do is to construct the intervals so that we are 95% confident that all the pairwise differences are simultaneously in their respective intervals. We need to manage the error So we need to modify our typical standard 95% confidence interval formula for the difference of two means. One modification is Tukeys formula. And Tukeys formula is a confidence interval. It's just one that's modified to control the error so that we can have 95% confidence on all three intervals at the same time. And that formula is... Now, the first thing we want to do is to find the margin of error, and one value there is MSE. Remember, in running ANOVA, we have to assume that the population variances are the same. MSE is a weighted average of the sample variances and is a good estimate of that common variation or that common variance. And we can get MSE from the ANOVA table. So we can see that MSE is going to be 0.669. So MSE equals 0.669. And the degrees of freedom associated with MSE, and remember that's in the denominator of the formula that calculates it, would be N minus K. And our total sample is 15. We had 5 cars for each type. And we had 3 treatments or 3 populations, and we have 15 minus 3 is 12. So there's our 12. Going back then, we have MSE equal to 0.669, and V, which is the degrees of freedom for the table, is equal to 12. The only other thing we need for the table, K, is equal to 3. Our value that we get from the table will be, let's go to this special table for Tukeys confidence interval. Notice that the columns are the K, so we have K equal 3, and the rows are the degrees of freedom. So that was 12, 3.77 will be our value. Now notice that because this is a balanced design, all the sample sizes are the same. In other words, NT is equal to 5. This margin of error does not change for any one of our comparisons. So what is my margin of error here? I will have 3.77 times the square root of 0.669 divided by 5. And that calculates out to 1.379. So that's my margin of error for my confidence intervals. Now I need to make the comparisons by comparing the sample means. And my pairs will be type G and type L, type G and type R, and then type L and type R. So I'm going to need those sample means to make those comparisons, and then I'll just simply add and subtract the margin of error. For type G, we have a mean or sample average of 34.92 miles per gallon. For type L, we have 36.56 miles per gallon. And for type R, 33.98 miles per gallon. So I'm going to take the L first because it's larger and that'll keep everything positive. So this value is 36.56 minus 34.92, and that's 1.64, the difference there. And then I'm going to compare type G and type R. So I'll take the sample means for those. I'll start with G and subtract the sample mean for type R. And this would be 34.92 subtract 33.98 and gives me 0.94. And then lastly, the sample mean starting with type L, subtract the sample mean for R. That gives me 36.56 subtract 33.98, or 2.58. So let's go back. 1.64 plus or minus my margin of error. 0.94 plus or minus my margin of error. Because the sample sizes are all the same, that margin of error does not change. And then 2.58 plus or minus my margin of error. And then my confidence intervals then would be 0.261 to 3.019 for type G and type L. For type G and R, I'd have a negative 0.439 and 2.319. And then for type L and R, I'd have 1.201 to 3.959. Now, with 95% confidence, these sample differences are going to be in their respective intervals. And with 95% confidence, alpha equal to 0.05, there is a significant difference between type G and type L, and there is a significant difference between type L and R. Notice the confidence intervals are positive on both sides here. Notice in this one right here, from type R to type G may decrease the gas mileage by 0.439 miles per gallon, or might increase the gas mileage by as much as 2.319 miles per gallon. So in some sense, this is inconclusive, because under 95% confidence, in going from type R to type G, I'm going to possibly decrease or possibly increase. So it's inconclusive. If I go from type G to type L, I'm going to increase my gas mileage anywhere from 0.261 miles per gallon to 3.019 miles per gallon. If I go from type R to type L, I'm going to increase my gas mileage anywhere from 1.2 miles per gallon up to 3.959 miles per gallon. Now, overall, what you can conclude, since there's a significant difference between G and L and R, we can look at these confidence intervals and conclude that type L gasoline yields the largest gas mileage. Now, one thing we could ask is, what is the average gas mileage for type L gasoline, in particular for this model of car? Then we can construct this confidence interval. Our formula would be, again, we're going to use MSE, and for us, the I would be an L, so we would have 36.56 was our sample average for type L. And then our degrees of freedom is still 12. So our degrees of freedom would be N minus K. And for us, that would be 15 minus 3 equal to 12. And if I go to the T-table where alpha is 0.05, I'm going to be calculating T alpha over 2, or T sub 0.025 with 12 degrees of freedom. I get 2.179. So 2.179 times the square root of 0.669 over 5. And that will give me 36.56 plus or minus 0.797. My confidence interval on the upper end would be 37.36. And on the lower end, 35.76. So I am 95% confident that the mean gas mileage for this particular model of car using type L gasoline is anywhere from 35.76 miles per gallon to 37.36 miles per gallon.